In this paper, we present OpenScene, a novel approach to perform zero-shot novel 3D scene understanding tasks with open vocabulary queries. Traditional approaches to 3D scene understanding utilize supervision from ground truth labels to learn specific tasks, for example, semantic segmentation with 20 pre-chosen categories. However, there are many other 3D scene understanding tasks where ground truth annotations are very limited, such as affordance prediction, material identification, and so on. Our key idea to address this broad set of applications is to compute a task-agnostic feature vector for every 3D point that is co-embedded with text and images pixels in the clip feature space. Then we can use the structure of the clip feature space to reason about properties of 3D points in the scene. How do we learn such text-image 3D co-embeddings? Given a point in a 3D scene and its corresponding post images, we first use state-of-the-art clip-based image semantic segmentation model to extract per pixel features for every image, and then use multi-view fusion with weighted averaging to project the fused features to 3D points. At this point, the fused features lie within the clip feature space, but may be noisy or inaccurate due to the limitations of single-view inference. To take full advantage of the 3D nature of the data, we also distill a 3D sparse U-net with a cosine similarity loss to predict the 2D fused features from only 3D point positions. Then, we ensemble the 2D fused and the 3D distilled features to a single feature vector for every point, as shown on the right. Now, with this feature, we can conduct a series of novel 3D scene understanding tasks. For example, 3D semantic segmentation without any predefined categories or training data. So given a 3D mesh of a Metapole 3D building, after our method produces features for every 3D point, they can be classified into semantic segments for any set of classes by finding the maximum cosine similarity to the clip embeddings of the class labels. This approach performs fairly well on common furniture classes. However, it really shines when the label set is larger and contains tail classes with few examples in typical training sets. For example, it finds the pool table in the house. This plot here makes the point quantitatively. The red bars on the left indicates a supervised approach performs better for the 20 classes with sufficient labeled training samples. However, all the remaining blue bars indicate our zero-shot approach performs better, especially when the training dataset is very limited. Zero-shot 3D semantic segmentation is just one application. In the following, we show other 3D scene understanding applications enabled by our approach. Here we show a real-time interactive open vocabulary search tool, where a user types in an arbitrary query phrase in the upper left of the screen, like floor or bed or toilet, and the tool colors all 3D points based on the similarities of their features to the clip encoding of the query. Yellow is the highest similarity, green is middle, blue is low, and uncolored is lowest. Amazingly, this works for words representing small real objects like teacup. And it even works for very specific objects like Snoopy. Even more interesting, it allows querying for scene properties in addition to object names. For example, it works for affordances like sit, where the tool highlights mainly chairs, sofa, and toilet. And it works for materials like glass, highlighting mainly windows and dishes. It can even get physical properties like fragile, where it highlights doors, decorations, and other trinkets. And size for activities like cook, where it highlights mainly the oven, toaster, and microwave. It's general enough to identify room types like bathroom, where it highlights all types of surfaces in the room. And finally, it even works for abstract concepts like festive, where it finds Christmas decorations. And all of these results were generated in real time without labeled training data from any 3D dataset. Thank you for watching.